This is the Chem 1 lecture for Ionic Nomenclature Part 1. This is just a quick reminder of the difference between covalent bonding and ionic bonding and the different terms. So we know covalent is two nonmetals, and we used these prefixes like mono, di, tri, and it was very straightforward. Just name what you see, or vice versa, write what you see. Ionic compounds are a little more complicated. So they have the metal bonded to the nonmetal. There's a transfer of electrons, therefore creating ions, positive or negatively charged ions. And so we're going to learn the naming system for ionic bonds today. Okay, so the hardest thing to break when we're dealing with metals and nonmetals, like an ionic bond, is we do not use the prefixes. It is not calcium dichloride. You're going to learn it's just calcium chloride. That 2 is there for balancing of the ions. So ions are obviously a big deal for ionic bonds, and so we're going to learn about univalent ions, and then we'll come back around for multivalent. But back in Unit 4 and 5, we talked about the charges that families would take to become stable. So univalent ions are atoms that only have one possible charge that makes sense. So for example, our alkali metals, group 1, they have one outer electron. They want to give away their electron, therefore the resulting atom is a +1. Group 2 would be +2. We've skipped kind of our D block area. I'm going to come back here in a second. Our nonmetals are -3, -2, -1, and 0. And then there's 3 elements that look kind of in what I call no man's land, like the D block, that do have a univalent charge. Aluminum is always a +3 charge. Zinc and cadmium are always +2, and silver is +1. So I call it the 3-2-1 staircase. So each time you step down, they're going down in charge. Notice that metals all have a positive ion. Nonmetals are negative. And that little staircase is also, if you put all of those like symbols together, it spells Katzenagel. I've always had a hard time seeing that. Katzenagel. Did I do that right? But don't forget about this diagonal, about the +3, +2, +1 for univalent ions. The elements in the middle of that periodic table that we skipped it up until now, they are called multivalent because they can have multiple charges. Elements that can have multiple charges. We're not going to ask you to memorize that iron could be a +2 or a +3 charge, but we do have to indicate which type of charge iron is being, and we'll teach you how to do that. But how we will symbolize the charge of the ion is through Roman numerals. So, for example, a copper 1 ion versus a copper 2 ion. So if you remember your Roman numerals, let's just review. We have I for 1, double I for 2, triple I for 3, 4 is IV, 5 is V, 6 is VI. So just like covalent compound, you name the least electronegative first, which will always be your metal. So name the metal first, then name your nonmetal. So we're going to teach you how to write ionic formulas first, and then we'll go back and name it. So for writing an ionic compound, you're going to need ions. You're going to need to have charges. And so it says write the symbols and put their charge next to them, the positive ion first. We're going to cross over them so that they're balanced. Rewrite the formula without charges. Make sure that the compound is neutral. Make sure that you are in the lowest possible ratio. So you reduce, which is very different than covalent, where you could have S2O4 and you are done. You're going to see a reduction of subscripts for ionic. Okay, so I think just jumping in will help see this. So sodium is Na, and based where it is on the periodic table, it would have a +1 charge to become stable. Sulfide is sulfur. This is -2. All ionic compounds are neutral. So right now, +1 and -2 don't equal 0. you would need another sodium. So now I have two positives and a negative. And so to summarize this, we would say Na2 with an S. That would be the proportion. For every 2 sodium ions, you're going to need 1 sulfur ion. And the formula would be Na2S. Notice I have no positives or negatives. Everything is simplified. Let's try aluminum chloride. Aluminum is in that 3-2-1 diagonal. Aluminum has always a +3 charge. Chlorine is a halogen. They want to gain 1 electron, so they're -1. We're looking for the charges to balance. And so, can y'all see that we're going to need a few more chlorine ions? And so to summarize that, it would be AlCl3. Let's do magnesium nitride. Magnesium is an alkaline earth. It gives away its 2 electrons. Nitrogen has 5, wants to gain 3. So the 2, 3, finding this balance is going to take a little bit. So if we do Mg plus 2, that's +4. This is -3. If I do this, now I'm at -6. So 2, 4, 6. 3 plus 3 is -6. So I have a total +6, a total -6. So I'm neutral. All ionic compounds are neutral. So if I had to summarize, I'm going to need 3 magnesium ions, and I'm going to need 2 nitrogen ions, or nitride, to become balanced. Now, there's technically a shortcut for what I just did, but we're sometimes nervous to tell you because you just do stuff without thinking about it. So if I was to kind of redo sodium sulfide, when you write out your charges, this is what your directions we're talking about, if you swap down the number to Na2S, isn't that what we got when we reasoned out how many ions were there? So aluminum was +3, chlorine was -1. I call this swap and drop. If the number is not there, you assume it's a 1. AlCl3. Doesn't that match? So, quote unquote, the shortcut is once you write your ions, you can swap and drop those numbers. The charges disappear. So the 3 swaps here, this one swaps there. We get Mg3N2. Okay, let's do a little more practice. This time we're bringing in our Roman numerals. So tin for oxide. So you have to remember that the Roman numeral is always giving you the charge of the metal. So tin is Sn. Metals are always positive because they lose their electrons, therefore they have more protons. And that's +4. Oxide is just oxygen. If you look at your periodic table, it's in group 16. They always want to gain 2 electrons. So reasoning this out, can y'all see we just need 1 more oxygen because then that's a -4 balancing with the +4. So +4, -4 equals 0. And so my formula would be SnO2. If you did the swap and drop way, you would have to be careful. +4, oxygen's -2. You swap and drop, you get SN2O4, and so it's actually swap, drop, and reduce. And so then you would have SN2O4. You would have to remember to reduce it down to SNO2. So swap and drop works most of the time, except when you have to reduce. That's something you could forget. Versus if you're just looking at your ions and the ratio, you can never go wrong up there. So you'll have to kind of practice and see what you ultimately feel comfortable with. So let's write a formula for copper 2 chloride. Copper is Cu. The Roman numerals are telling you the charge of copper is Cu plus 2. Remember, the periodic table would not tell you that. That's the multivalent zone. I call it the no man's land. Chlorine is a halogen. All halogens have a -1 charge. So if I do a swap and drop, I'm going to need 1 copper ion. I'm going to need 2 chlorine ions for this to be balanced. So notice in my final formula, all my numbers are low and there's no plus or minuses. And then last one, silver bromide. So silver is Ag. And if you find it on your periodic table, it looks like it's in no man's land, the multivalent world. But remember our 3-2-1 diagonal of aluminum, zinc, and silver. So silver is monovalent. It always has a charge of +1. Bromine's a halogen, -1. Here our charge is already balanced to 0, so we just need one of each of these ions, A, G, B, R. Okay, so now we're going to do the opposite, and we're going to name ionic compounds. And so here is a different system than covalent. Remember, we are all in the ionic world today, metals, nonmetals. So throw out prefixes, mono, di, tri. When you're naming a metal and a nonmetal, because that's ionic bonds, you're going to name the metal first. If it's univalent, then you're done. Just name the metal. We'll talk about multivalent in a moment. It deals with Roman numerals. And then your second element, your anion, we're going to change the ending to IDE. So that is similar to the covalent system. So univalent, meaning they're always the same charge. So K, if you look at where K is on the periodic table, it's an alkali metal. So that family always has a +1 charge. So we're just going to name it potassium. And then P is phosphorus, and we'll change phosphorus to phosphide. Al2O3, aluminum, if you look where that is on the periodic table, it's in that 3-2-1 diagonal, so it is monovalent. Aluminum's always 3. And then oxygen changes to oxide, aluminum oxide. Na is sodium. Sodium's also an alkali metal, always +1. And then nitrogen changes to nitride, sodium nitride. And then Zn looks like it's in no man's land, that multivalent box, but it is part of that 3-2-1 diagonal. Zinc's always a +2 charge, so there's no need to tell me Roman numerals. It would just be zinc iodide. Okay, this to me is by far the hardest part of all the nomenclature, and then specifically ionic nomenclature. How do you name metals that have multiple charges? So if you look where iron is on the periodic table, it falls in what I call no man's land. It doesn't have, so here's no man's land. It doesn't have a set number. It can change. So we have to say what type of charge iron is being. So the basic of this is it's going to be the metal iron, a certain charge, and then sulfur changes to sulfide. So kind of like last page, metal, nonmetal goes to IDE. What's different are these Roman numerals, and that's where things kind of get tough, but totally doable. So we would recommend that you start by finding the total charge of the negative by using the periodic table. So for example, sulfur, according to the periodic table, has a -2 charge. And I'm going to divide the metal and the nonmetal. Okay, except it said total. So there's, each sulfur is -2, but there's 3 of them. So like if you literally drew out 3 sulfur ions, that would carry a -6 charge. We know ionic compounds have to equal 0. They have to be neutral. So that means our positive charge must be +6 to balance it. But I have 2 irons to split that +6 charge. So 6 divided by 2 would indicate each iron is carrying a +3 charge. So the official name for this would be iron 3 sulfide. So let's practice that. So like I said, this stuff is you have to be looking at your periodic table to even see, does it need Roman numerals, does it not need Roman numerals? So CuBr, Cu lands in no man's land, so it's going to be copper something bromide. We find the metal's charge by working backwards. We know bromine is -1. The whole thing has to be 0. There's only 1 bromine, so my charge is still -1. There's only 1 copper, so that's a +1. This is copper 1 bromide. And a lot of times y'all ask me, like, do you still have to write the 1? Yes, because copper doesn't always have a 1 charge. So we have to be super clear that in this bond, copper has a +1 charge. MnF3. So we know Mn is manganese. If you find Mn on your periodic table, it's in what I call no man's land. It's in that center of the periodic table. so that this needs Roman numerals, so it's going to be manganese something, and then fluorine goes to fluoride. So once again, work backwards. We know that one fluorine ion is -1, but there's 3 of them, so I'm going to multiply that and get a -3 total charge. We know the whole thing has to balance to 0. So that means the overall positive must be a +3. There's only one manganese, so that one manganese must be carrying a +3 charge. Okay, let's try SnO2. We know that Sn is 10. If you look where Sn is, it's near that staircase on the periodic table. And so it falls under here. That is still what I would call multivalent, no man's land. So it's going to have a Roman numeral, and then oxygen goes to oxide. So what do we know about oxygen? One oxygen takes a -2 charge, but how many oxygens do we have? We have 2 of them, so that's an overall -4 charge. So therefore the overall positive must be +4. There's only one 10 to carry that. This must be 10,4 oxide. All right, we got 2 more left. Move this around. Pb, anyone remember who Pb is? Lead. Pb is also in that staircase region. It's considered multivalent. So lead something phosphide. Okay, work backwards. What do we know about P? On your periodic table, it carries a -3 charge. But how many do we have of them? There's 2 of them. So like literally imagine there's 2 phosphide ions floating around. So that creates a -6 total charge. Therefore, to be balanced, there has to be an overall +6, but there's 3 lead ions. So each lead, if you use 6 divided by 3, each lead would have to be carrying a +2 charge, 2, 4, 6. So this is lead 2 phosphide. And last one, we have cobalt. Take that time, look on the periodic table, it falls in the middle. If it's in the middle, it needs Roman numerals. So work backwards, we know nitrogen is a -3, there's only one of them, there's only one cobalt, so this must be cobalt 3 nitride. This does conclude the Ionic Nomenclature Part 1 lecture. Please, please, please practice. Use that periodic table and you can do it.